Okay, we're going to continue. Can you listen to me? Can you listen to me, somebody?
Yes, doctor.
Yes,
Yes, doctor.
Okay.
Yes.
Can you see this? This Word document? Can you see the Word document, people?
Yes, doctor.
Yes, doctor.
Okay, thank you. Okay,
Yes.
let's see if we can do this. Okay, so first we're going to do an introduction to the finite element method discretization. Okay, in general, we have to assume what we call the continuous hypothesis. So this means that instead of accepting the atomic, see, for example, if you accept the atomic theory of matter, see, this is like atoms, okay? Okay, but here, this is empty. Okay, so if you ask me what is the stress, for example, if this were part of an structure, if you want to calculate the stress in this empty space, the answer will be 0 because there are no stresses, there are no matter pressing to each other because this is empty. So instead of this, what we do is we accept the continuous hypothesis. And we assume is that if we have this piece, in this case, the matter will be continuously distributed. Continuously distributed. This means that now there are no spaces inside here, and we can go on and calculate continuously the stress inside this space, this matter. Okay? We can say now, we may calculate stress in any point in the system. Okay, so if we accept this hypothesis, it's an assumption. Instead of seeing matter in this way, we start seeing matter in this way. If it's like assuming that it is continuously distributed in the space. Okay, and now, of course, we can calculate the stress in any place we want. Now, after doing this assumption, okay, we can go on and, for example, we can calculate the solution of a beam problem. Don't worry, I'm not going to solve it right now, but in the future. For example, let's suppose that we have something like this. This is a beam. I still don't have much of a practice using these things, so please be patient with me. We have something like this, and we put here a support. And let's suppose we have a load here, a concentrated force like this. Okay? If we solve this thing, we employ the correct boundary conditions and the ends. Okay, this is this 1D problem has a continuous solution. So for example, let's call it V of X. If we find the solution of this problem, of course, you can remember that, for example, the solution will be something like this, right? No slope, no deflection, something like this and there. So in every point, we can obtain the value of V. Okay, now we go on. But this is a function, this is a continuous function. What do we mean by this? That means that we can evaluate this function in any point that we want and obtain a value for the deflection. Okay, so for example, I said V at 0.500001, and we get a value, and we can evaluate this and another point, 5 point. I have 4 zeros, 2, 3, 4, another one, and another 0. And see, this is very close to this, but I obtain 2 values. This is different than this one. Why? Because we have accepted the continuous hypothesis. Okay, so we can evaluate in any point where we want. So this is the result of the continuous hypothesis. What else? This function is continuous. That means that we have an infinite number of value for V. This is, we have an infinite number of values of the V. Okay? Now, this is a continuous problem. Now, at the beginning, I said that this is an introduction to the finite element method discretization. Okay? So instead of trying to solve, so this problem like here, trying to find V of X, we're going to try to find a similar problem, but which includes only a discrete number of unknowns. That's a discretization, okay? In a discretization, we try to solve a problem with a discrete, let me put it like this, discrete number of unknowns. This is U. So here, we are saying that an infinite number of unknowns. Here, we are saying that we are going to find only a discrete number of unknowns. Of course, if we try to find, for example, 5, 10, 100 values, it's easier than to try to find an infinite number of values of V, or trying to find a function of V. Because in many cases, this solution is extremely difficult to find or doesn't exist. Okay? So let's go on and say a couple of words about the discretization, specifically in the finite element method. Okay? So we say in the finite element method, okay, finite element method, the discretization okay, the discretization has two phases. Includes two phases. Okay, in the first one, we partition the domain. So here, for example, in the case of the beam, okay, the domain goes from 0 to L. So the domain and try to find V, which is evaluated or might be evaluated from 0 to L. That's the continuous problem. Now, in the case of the finite element, instead of doing that, we partition the domain. Okay, so instead of taking that, so we said, okay, this is the beam. Okay, this is X. Okay, in this direction, we measure V. This is 0. Okay, let's include it, the supports. Here is the load, F. So this is the system. Now, instead of doing that, let me change color, and we're going to partition the domain. So instead of taking the whole thing, we partition there and say, okay, we're going to partition here. So we're going to go from here to here, and from here to here. So this is the first partition, and this is the second partition. Each one of these partitions, we call it a finite element. For example, we can call it number 1, and this is finite element number 2. So we're going to consider what happens in this and also in this. And of course, you can think that instead of partitioning this domain in 2 parts, we can partition in, I don't know, 5 or 10, whatever parts. Yes, we can do it. And of course, we're going to insist on that because that means that the solution will be closer to the real one, to the exact one. But this is just an approximation. Now, what else? It's very important that each one of these elements is defined using these points, okay? And these points is what we call joints. Okay? In Spanish, this is nodos, okay? In English, it's joints, okay? So in this case, we have 1, 2, 3 joints, and these 3 joints help us to define 2 elements. Okay, so we see that the domain is partitioned. Okay, I'm explaining this with the simplest case of a 1D problem. Okay, so that's the first step. Now let's go to the second step. And the second step is what we call an interpolation. So we said, okay, in every element, okay, we interpolate the function with the values of the joints. Okay? So first is we partition. And after we partition, we start looking at what happens in the joints. Why? Because at every joint, we're going to have an unknown. And what we do is we assume an interpolation in every element. Please, this is every element. And what we do is we interpolate the values in every element using as a reference the values at the joints. Okay? I think we need to. Are you with me, people? What do we mean by this? Interpolation from each element. Okay, for example, in the case that we are explaining here, okay, let's suppose that, let me change color just in case. There. See, for this element here, no, let me use the other one because here I have 0 here. Let me use this value here. So for this element here, okay, element 2, you see that this node, this joint, will come downward, right? So let's suppose that this is a value, okay, let's call it D1Y, and let's put it a little hat here. I will explain that in. So I'm sorry, there. What else? We notice that this joint will also rotate. Okay, so this point comes downward, and also this region rotates. So it's go like this. Okay, so this angle, we call it phi1z. There. So we have 2 values. Now, let me elongate this to facilitate. So this and these are the joints which define this element. Now, oh, come on. Okay, now, in this joint, I see that there is no deflection. So the deflection here, let me put it D2Y, that's 0. And also, let's suppose that here we have a rotation. So the rotation will be like this. Well, let me erase because otherwise I'm going to get in trouble. Okay, there. So this is the rotation, a large rotation, of course, so you can see the deflection, the difference there. And of course, we have said that the deflection is 0 here because we have a support here. Now, we have 1, 2, 3, and 4 values. But here, we do not nothing. So what we do is we interpolate from here to there. That means that we are going to develop something like this. So we start in this point, and we move in this direction following the slope there. Now here, we have to end here, and also we have to end with this slope. So we have to end here. There. So this, oh shoot, come on. I need to practice to use this thing. There. So this function is an approximation. Remember, let me go back. If we solve this problem, we find this V. Okay? This V is exact. Here, we are interpolating, okay, from here to there. But the problem is that the function that we are going to use in order to interpolate is not necessarily equal to the exact solution. So we can say that we can express this interpolation in the following way, okay? We can interpolate using okay? So we use this notation and multiply by, okay, you see that this is a row and this is a vector. What's the product if you multiply a row times a vector? Somebody, what's the result of multiplying a row times a vector?
Row.
No.
Vector.
If you, and a scalar, yes. If you multiply this row times this vector, the result is an scalar, and this is an scalar. So here, in this row, we're going to have 4 elements. And here, we're going to have the 2 displacements and the 2 rotations. So here I'm going to have D1y, Phi1z, D2y, and Phi2z. And here I'm going to have N1, which depends on X, N2, N3, and N4. So you multiply this vector times this row, and the result is going to be V of X. Question for you: how many unknowns do we have right now?
3.
Exactly, because D2y is 0. So we have 1, 2, and 3. We suppose that these functions for interpolation can be expressed completely. So this is known, and these are unknowns. How many? 3. Okay, so we see that in this element, we have 3 unknowns. Okay, so the explanation that I'm trying to give you here is that we have converted the solution of the problem from this one here, okay? In this case, this problem is a continuous problem. So we have to try to find this V of X, which solves this problem continuously. And instead of that, because we consider that this is a very difficult problem, instead of that, we're going to solve something like this. And in this case, we have how many unknowns? 3. This is a discrete number. So we can say that we have converted a continuous problem into a discrete problem. Now you tell me, wait a minute, what happens with the first element? Yes, in the case of the first element, this one here, we also are going to have some unknowns. But in general, if we assume the interpolation, okay, in general, we can see that these are going to be the unknowns. The unknowns in the finite element method are going to be, in general, the values at the joint, okay? But we have to complete this process. We have to specify what these functions are, and also one thing is saying something like this, and another thing is trying to set up a system of equations, okay, in order to find the unknowns. Okay, be patient. Be patient. We're going to explain how to do it. But right now, the message that I want to give you is that instead of solving a continuous problem, trying to find a continuous function that satisfies equilibrium, we are going to try to find these unknowns, and the number of these unknowns is a discrete number, in this case, 3. And something else before we break is that this is an approximation. This is not the exact function, okay? This is just an approximation. If we use a very small number of elements, of course, the approximation is not going to be very good. As we increase the number of joints, okay, the size of the elements is going to be smaller. And as we increase the size of decrease the size of the elements, the approximation to the correct solution is going to be closer and closer, okay? That's something that we call convergence. We're going to discuss that in a minute. Well, not now, during this first chapter. People, before we break, is there any questions about what we have said? Any question?
Doctor.
Okay, go on.
I have a question.
Go on.
My name is Bias.
Okay, go on, Bias.
This function is approximate. I create the function? Or...
Yes. See, what happens is this. You're saying is that this is an approximation. And if you are saying that you are interpolating, you have to evaluate this in this point, and you have to recuperate this value. Also, you differentiate this and evaluate it in this point, and you have to obtain this value. Again, you evaluate this in this point, and you have to obtain this value. And finally, the derivative evaluated at this point has to recuperate this value. And in this way, we can set up these 4 functions. So this is completely known, and we will see that, okay? Yes, so this is known completely. 4 unknowns. This is a number of unknown is discrete. That's why we call this process discretization. Bias, did I answer your concern?
Yes, doctor. Thank you.
Okay. There was another question, somebody else?
Yes, doctor. The 4
unknowns.
N1 of X.
Okay,
no.
this one here.
Yes.
Okay.
I didn't understand what does that equations represent.
Okay.
Why are they 4?
Because we have to multiply each one of these by each one of these. So you multiply D1 by this, Phi1 by N2, D2 by N3, and Phi2 by N4. And the result of this product is going to be one single function. This is an scalar. So each one of these, but go on.
What does each one is, what are each one? I mean,
don't worry, we will separate. I can give you a hint, okay? We're going to say that this is going to be equal to A1 x cubed plus x2 x squared plus A3 x and plus A4, right? And since we are interpolating, we have to satisfy A1, 2, 3, and 4 will be found such that V evaluated at this point has to be equal to what? D1y. You differentiate that and evaluate it at this point, and you have to recuperate this angle. And you also, you have to evaluate the function and the derivative in this point, and they have to recuperate D2 and Phi2. So you have 4 equations, and you can solve, you can find A1, 2, 3, and 4 to set up this equation. And then what we do is we can write it in this way. And don't worry, we will go in detail in the next session. And at the end, we're going to be able to identify what is N1, 2, 3, and 4. So these functions, these 4 functions are completely identified, completely specified. So this is completely known. N1, N2, N3, and N4 are completely, in this case, in the case that I'm explaining, for beams, it's cubic polynomials. Ms. Freire?
Yes, doctor,
Okay.
thank you.
Okay, people, so I'll see you Thursday. And please don't forget that you have to start trying to get the certificate from the Ministry of Health Service, Public Health, and you have to send those PDF certificates to Genesis. She will collect, and at the end, we will be completed the first step to be able to receive permission to come to campus. Bye-bye now.
Thank you, doctor.